This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll go over PV diagrams, which stand for pressure volume diagrams. First, we'll look at internal energy and go over an important equation, and then we will look at the 4 PV processes that you need to know for the test. Internal energy is basically the kinetic energy of a gas. So the higher the internal energy, the faster the gas particles are moving. So in other words, if internal energy goes up, then the temperature of that gas also goes up. We are focused on how the internal energy of a gas can change. And there are 2 factors. First is Q, which is heat, and then W is the work done by the gas. So first, let's look at heat and talk about how we know if heat is added or taken away from a gas. For all of this discussion, we need to look at the image that we have on the right, which this is a piston that is filled with gas. So this area here is filled with gas molecules. And then on top we have a piston. So this piston can move down and up depending on what forces are involved. We discussed heat in a previous video, and heat is the transfer of thermal energy. So if we wanted to add heat to these gas molecules, we could light, let's say, a fire underneath of the piston. And if we had a fire underneath the piston, then those gas molecules are going to be heating up and they're going to be gaining thermal energy. So Q would be positive in that instance. Conversely, the gas molecules could lose thermal energy. So thermal energy could be lost by the gas if the gas is hotter than the surroundings, and assuming that gas is also not insulated. W refers to the work done by the gas. And work is the term that we use to discuss energy transfer. And the units for work will always be some unit of energy. So if the gas does work on something else, then the gas is transferring its energy to something else. If work is done to the gas or on the gas, then energy is being transferred to the gas. And we're going to look at our example here to show how a gas can do work and how work can be done on a gas. So if we say this piston here is movable, and that these gas particles are bouncing around, they are exerting a force upwards on that piston. And if they can exert enough force on that piston, then the piston is going to travel upwards. And the equation for work is W equals force times distance. So if that gas and that piston expands, it exerts a force on that piston, and then whenever the piston moves up, that force gets multiplied by the distance the piston moves, which then gives you the term work, and that is how much work the gas did on the piston. And whatever value that is, that gas lost that much energy. The opposite would be true if the piston moved downwards. So let's say that someone pushes the piston down. So now the piston is moving downwards. And now the piston is exerting a force on the gas molecules. And over the distance that the piston moves downwards, again, we could do force times distance equals work. But now this would be work done to the gas. So this time the energy would be gained by the gas. We said that when the gas expands, it loses energy. So if we look at this equation, we need our term W to be positive so that we're subtracting a positive number. So when the gas expands, our work term will be a positive W. When the gas is compressed, we said that the gas will gain energy. So we need to have this negative W term end up being positive. So then that will be a negative work that's being performed on the gas. So then when we plug that into the equation, we end up adding energy and changing our delta U in a positive way. The last thing we'll look at is PV diagrams. And it's taking what we just talked about before and then applying it to these certain situations. So we're going to zoom in on each one of these and go through them step by step. For each one of these, we need to keep in mind the piston idea that we talked about before and the equation. And we're going to go over what happens with the work, the heat, the internal energy, and the pressure during all of these processes. Each process has one variable that's not changing. And that variable that's not changing usually tells you some really important information. So always first analyze that. In our first one on the left, this is an isothermal process, which means the temperature is not changing. And earlier in the video, we said that U was the internal energy. And the internal energy is basically the kinetic energy of the gas, which is directly correlated to the temperature of the gas. So if the temperature is not changing because it's isothermal, then that means that the internal energy is not changing. So then delta U would be equal to 0 because it's unchanging. The best thing you can do next is think about what happens as we go to the right on our graph. So as you go to the right, the volume of the gas is expanding. And remember what we said earlier about when a gas expands, what that says about the work that the gas is doing. We said that the gas will lose energy as it expands. And that means that if you look back at our equation, that we need W to be positive. So that way, whenever we plug that value into that equation, the internal energy goes down because the gas loses energy as it expands. And that doesn't just apply to a gas that's in a piston. Even a gas that is out in the open, so just out in the air, if that gas starts to expand, it's exerting that force on the gas molecules around it, so it is still doing work on the surrounding gas particles in order to expand. So even not in a piston, anytime a gas expands, it is doing work on its surroundings, therefore it is losing internal energy. Next, we'll analyze what happens to Q. And now we actually have two of our variables in this equation already figured out. We know that delta U has to be 0, and we know that we're going to be losing energy through the negative W. So in order for delta U to remain 0, our value of Q has to be equal to the value of W. So Q will be positive because we're going to be subtracting W. So Q needs to be positive and it needs to be equal to the value of W. So Q equals W. Finally, in order to plot this, because we have our pressure on the y-axis, we need to think about how does this all affect pressure. And what we need to think about is that pressure is the result of all of the collective collisions of the gas with its surroundings. And we said that the internal energy is unchanged. So the gas is moving at the exact same speed, and we have the exact same amount of gas particles that we started with, and that's assumed for all of these processes that the number of gas particles doesn't change. So if the speed of the gas is unchanged, but as you go to the right, the volume has gotten larger, think about what has happened to the number of collisions. So with a larger volume, but moving at the same speed, the number of collisions has actually gone down. So pressure will decrease as long as the volume is increasing because the collisions are going down. So pressure goes down as we increase volume. And if you were to move backwards, so if you were to think about this whole process as volume decreased, then all of this would be reversed, and then your curve would go the opposite direction. Next, we have an isometric process. So based on the name, we know that the volume is not changing. The volume corresponded to the work. So since volume is not changing, the work will be 0. So we're going to have a value of 0 for work. And that means that on our x-axis, we're not moving left or right. So your line is just going to be vertical. In a problem like this, they would tell you if the pressure was increasing or decreasing. Let's just pretend that the pressure is decreasing. So we're going to show that vertical line pointing downwards. And now we can think about what happens to the rest of our variables. So we know our gas occupies the same volume as before, but the pressure has gone down. So that means that the number of collisions that the gas particles are making with the surroundings has gone down. And the only way that could happen if the volume remained the same is that the gas particles themselves are moving more slowly. And that would mean that our internal energy went down if the particles are moving more slowly. Now we have two parts of our equation. We have U and W. So if W is 0, but the delta U went down, then that means that Q must be negative. So our gas lost energy through heat loss. And then the pressure went down, and that was just our choice for this example. If the pressure went up, then your logic would be the exact opposite for each one of those variables. In an isobaric process, the pressure is not changing, so you can draw just a horizontal line across. We said earlier that thinking about the change in volume and how that affects the gas is one of the best places to start. So we're going to think about if volume is increasing, so we're moving to the right on our x-axis, and you could think about this the other way and move to the left. We're just choosing moving to the right to keep things consistent. So as we go to the right, the volume's increasing, which means that the gas is doing work on its surroundings, so we need W to be positive because the gas is losing energy. So we want to subtract a positive number in our equation. Here's where it gets a little bit tricky, and the way you want to think about this is that the pressure is unchanging. So the pressure did not change. I'll just draw a horizontal line to show no change in the pressure. This means that even though the gas expanded and is now occupying a bigger volume, it is still able to maintain the same pressure as before with the same number of gas molecules. And the only way that it can maintain that same pressure at a larger volume is if it's moving at a faster rate, which means that our delta U went up. So it had to gain internal energy, so delta U was positive, or delta U went up. And the only way delta U could go up if we lost energy through the work that was done by the gas is if Q was positive and if Q was more than W. So heat was added to the gas in order to keep up the same pressure as we increased the volume that the gas was occupying. The last process is an adiabatic process. An adiabatic process means that there is no heat exchange. So right off the bat, we know that Q, the delta Q, or the change in the heat, will be 0 because there will be no heat exchanged. Now think about, as you move to the right on the x-axis, what is happening to W. And just as before, as the gas expands, it's doing work on its surroundings, so W needs to be positive to show that we're losing internal energy. We now know what happens to our two variables in the equation for delta U. So if you plug both of those in, and you plug a 0 in for Q, and then any positive number in for W, then you can see that your delta U will be decreasing. So delta U goes down. Now we just need to think about what happens to our pressure. Our gas is occupying a larger volume, and the delta U went down, so the gas is moving slower than it was before. So just try to think about, what does that mean for pressure? That means that the pressure has dropped drastically. So it's a very drastic drop, and the curve looks somewhat similar to the isothermal curve, but it's actually an even steeper drop. And that's because in the isothermal and in the adiabatic process, the gas is occupying a larger volume, but in the isothermal process, it was the same temperature the whole time. But in the adiabatic process, we showed that the temperature went down, so the gas molecules are moving even slower than before. So that pressure drops pretty drastically. For the test, you don't necessarily need to be able to think through all of these. I would make sure you are very good at thinking about what happens to the internal energy of a gas when it expands and what happens when it is compressed. Practicing that thought process on these 4 processes is an incredibly good way to do that. So if you can explain these 4 processes, you should be in a really, really good place in terms of thinking about the internal energy of a gas. The last thing we're going to do is look at how you find the work based off just the pressure volume diagram. And first we need to look at this equation, work equals pressure times the change in volume. And this equation is just a derived equation from work equals force times distance. And we're not going to look at how you derive it from that. You don't need to know that, but just know that either one of those equations are perfectly valid for work. And what that equation allows us to do is use the area under the curve to find the work done by the gas. So if we look at our isobaric process on the left, I have put some grid lines on here to show us what these values for pressure and volume are. So the pressure for this one would be 9. The volume changed from 5 to 15, so the delta V would be 10, giving us a total work of 90. And so what we basically did was we actually just found the area under the curve because the height was 9 and then the length was 10. So the area under this curve was equal to the work done by the gas. And that's if your volume was increasing. If the volume was decreasing, then that would be the work done to the gas. It's really straightforward whenever you have an isobaric process because that pressure is just a horizontal line. But if you look at our isothermal process, the pressure is constantly changing. And the only way to truly accurately find the area under that curve would be to use calculus, but luckily calculus is not on the MCAT. So the best thing we're going to do is an approximation. And how you do that approximation, you want to start just by drawing your vertical lines down, and then turn that into a rectangle, and then a very approximated triangle. And then from there, you would find your area of the rectangle first, and then the area of that triangle, and add them together. Just keep in mind that that triangle, that is not the actual area. That's not going to be an accurate area, but it should get you at least close enough that you could compare it to one of the answers if you ever have a question like this on the test.